Okay, in this lecture, I just wanted to talk a little bit about Legendre polynomials, and in particular, I wanted to go over them using Mathematica because it's kind of nice to be able to plot them and see what they look like. And just to remind you, they're related to kind of what we did before. They're related to this idea of orthogonal functions, and a set of orthogonal functions like these sine functions, being able to build different other mathematical functions. So let's go down here and look at the Legendre polynomials. I just want to start out by showing you that Mathematica knows about the Legendre polynomials, and you can write out as many terms as you want. Here I'm just writing out the first six in a particular table format, so they're easy to look at. And this is the general Legendre polynomials, which means they're just being evaluated at x. Okay, so if I look here at what I'm doing, this table, if I get rid of this, you'll see kind of what it looks like. It just makes a list. Right now, it's making a list of two things. There's n, so it's kind of making a list of a list. The first variable is n, the value of n that's being used, and then the second variable is the actual Legendre polynomial for that n value. Okay, so the built-in function is called Legendre polynomial, n. You have to input n for the one that you want, the term that you want, and then this one depends just on x, so that's why we're getting x's in here. The one that we used for spherical solutions to using separation of variables depended on cosine of theta. So I'll show that in a second. So this just lists the first six, and then if I do this table form, it just makes it look a little nicer when it outputs. Okay, so these are the first six. So just like we showed before, the zero, so when L equals 0, the Legendre polynomial is just 1. When L equals 1, it's x, and then it gets more complex as you go to larger and larger L values. Okay. Here I'm just plotting those first six. Again, these are the general Legendre polynomials. So I got rid of the table form thing because that makes it so you can't plot it nicely. So now this is just the list of the first six, and I also got rid of this n part because that would have screwed it up. So it's just the list that just has the Legendre polynomials. So each one of these terms is a Legendre polynomial, and I can plot them all together by just putting this list in to my plot command and having them plot from -1 to 1. Okay, and then all the rest of this stuff is just making the plot look pretty. And this is what you get. So the 0, L equals 0, it's just equal to 1, so you get this straight line. This is when L equals 1, you just get a line with a slope of 1. Okay, and then here's 2. So you can see as you go to higher L terms, you're getting more complex, higher order polynomials, just like what we would expect. They're kind of fun to look at. Okay, so similar to what we did above, we can prove that the Legendre polynomials are orthogonal by plotting the product of two and observing there's an equal amount of area above and under the curve for our range of -1 to 1. Okay, so here again, I'm just defining two functions to be the Legendre polynomials with different values of n. In this case, I call it n and m because that doesn't matter. And then I plot the two, the product of the two down here. So you can see as long as n and m are different, okay, so I can even make these really high order. I'm going to get something crazy. As long as n and m are different, you end up getting something that's going to integrate to 0. You can see that when I plot it out because there's as much area above and below the curve. But you can also see when I just do the integral here, you do in fact get 0. Okay, again, however, if I were to plot these functions for the same value where n is equal to m, in that case, I don't get something that would integrate to 0. I get something that integrates to something else. So in that way, it's a lot like our sine functions. They're just different. They're more complicated functions than just a sine function. Okay, so now we're going to think about Legendre polynomials evaluated instead of at x, but at cosine of theta. That's what we did in order to separate variables for our spherical version of Laplace's equation. And that just came out of solving the ODE. When I did the solution for different L values, it was following this function here, where here again I've plotted the first six Legendre polynomials. And this is what looks like, what the solutions looked like for the different L values of the general solution that we came up with for Laplace's equation, okay? I can plot these again. That's what I'm doing down here. They look a little bit different, again, because now we're evaluating the Legendre polynomial at the cosine of theta, okay? And I'm also just plotting it from 0 to pi. But here you can see the 0 with order 1. It looks like 1. There we go. The 0 with order 1 looks like 1. Screwed that up. The first order 1 looks like cosine of theta, so that's the blue line here. Okay, the second order 1 looks like this function here. That ends up looking like this curve, okay, and so on and so on. So the higher order ones are getting more complicated. We can also prove that they are orthogonal over the range from 0 to pi, but now we have to multiply by sine of theta because we've changed variables. So when I change the variable from evaluating this Legendre polynomial at x to changing it to the cosine of x, I have to also change variables within the integral. So up here, I was doing, let's see if I go here, yeah, I was doing the integral with respect to x. Now I want to do an integral with respect to theta. So I have to change variables. When I do that, that's going to give me an extra sine theta term, and it's also going to change my integration limits from 0 to pi. Okay, so that's a little bit differently, but I can come down here and I can do the same thing. I can pick any two n and m, and I can evaluate this, and we can see what we get. Okay, again, here, these are the functions. I'm evaluating them at cosine theta. And the difference is when I'm plotting, I'm also multiplying the product of these two functions by the sine of theta. If I do that, you can see as long as n and m are different, I get equal amounts of area above and below the curve, okay, even if I go over to really high orders. But if n and m are the same, then I'd get something that wouldn't integrate to 0, okay? So we can play around with that. So here, and again, I am doing the integral, so that is 0 there. And if I make them both 5, I get a different answer.